Okay, in this video we are going to start talking about the other parts of the atom that we haven't looked so much at, and that is electrons. So let's pick up just a really quick reminder of where we were with experiments led by Rutherford, somewhere in the neighborhood of 120 years ago-ish. He gave us a lot of information about the understanding where protons were located, how they were kind of distributed or not so much evenly distributed throughout the atom, but he didn't tell us much about electrons and why they move the way they do and why they aren't just sucked in by the large positive charge of the nucleus, which is what we would kind of expect to happen. So let's figure that out. The first thing that's kind of important information to know about electrons, because electrons are highly energized little bits of matter. There are all different kinds of energy in the world, and we are going to talk primarily about electromagnetic radiation, or EMR. This is a transfer of energy or a movement from one place to another via a specific type of energy called light. There are all kinds of different sources of light and places where light can be found to contain electromagnetic radiation. Some of those sources that you might be familiar with are X-rays. So X-rays are actually an energy source that involves light. There is UV light or sunlight or tanning bed light. We're going to focus though on visible light. The term gives you kind of a clue about what it is. Visible light means the range of energies within EMR that our eyes can process and actually observe. So the ways that electromagnetic radiation or visible light travels through the world is it travels in kind of a wave-like pattern, sort of like a water wave or a sound wave, if you're familiar with those ideas. The thing that's interesting about light is that it travels at a very consistent speed, and this program, once again, has dropped off my exponent, so this should be 10 to the 8. Light travels at a speed of about 3 times 10 to the 8 meters per second, which is obviously very, very quickly. And that is consistent regardless of the color of the light, the type of the light, whether it's UV light or X-ray light. It all travels at the same approximate speed. What is different from light source to light source are the characteristics of the waves themselves. So the first feature is called wavelength, and it's exactly what it sounds like. It's how long a wave is from peak to peak, this distance. We usually measure it in meters. I mean, meters would give you an exponent that is quite small, or even more specifically in nanometers. And we often use a variable to represent this idea of wavelength, and we use this one. It's a little Greek symbol. I believe it's a lambda, actually, and it is shaped sort of like that. So that's the symbol for wavelength. The other feature of waves that we talk quite a lot about is frequency, or how often the waves pass a certain point. A lot of times we're looking at this in terms of a second. If we count 1 second, how many waves go by this particular point in 1 second. And so it's often measured in waves per second, or in this value called hertz. It looks like it got chopped off a little bit. Hertz, which is abbreviated HZ. It's named after a German gentleman named Heinrich Hertz, who did some of the early work on wave frequencies, and so the constant, or the unit was given his name. We represent frequency with this letter. It looks like a V. It actually has a little lead-in tail, but that is the variable that we use to represent frequency. And we can explain the relationship between wavelength and frequency by looking at this equation, where C represents the speed of light. If we multiply the wavelength by the frequency of the waves, that will give us the speed of the electromagnetic radiation. And again, I told you that the speed of light is constant. So what we are really looking at here is just the fact that these two values are inversely proportional. As your wavelength increases, the frequency decreases. And you can see that in this picture here. As the wavelength increases, so we're at this end, long waves, the frequency decreases, right? It takes longer for one wave to pass this point. As the wavelength decreases, the frequency increases. So when these waves are short, they pass a given point much more quickly. Down here you can kind of see the spectrum or the range of colors within the visible light spectrum and how long their wavelengths are. So the lowest wavelength of light is violet at approximately 400 nanometers, and the longest wavelength of light is red at about 700 to 800 nanometers. The thing that's interesting about light and really all electromagnetic radiation is that within the wave that's traveling, there is a certain amount of energy being transported along that wave. So you can kind of think of it, if you're thinking of a surfer, like in this picture, right? The surfer is transported from one part of the wave to another, and he carries with him a certain amount of energy. That's kind of the way that light works as well. There's an effect that was described first by Max Planck, who is a scientist. I believe he's also German, although I could be wrong. He was doing some work right about the turn of the last century as well, and he described the photoelectric effect. Photo represents light, electric is energy. So he said that when different kinds of light shine on a metal object, the energy carried in the light will cause the emission of an electron to be released from that metal object. We can't see that electron release. Remember, electrons are super teeny tiny, but it can be detected if you put some kind of a shield or a screen around the metal object itself. Then we can detect electrons hitting that screen or object. In doing more research and more experimentation, he eventually defined energy. So if we think back to our little surfer guy, he said this little guy, if he were traveling on an an EMR wave, he would be a little packet of energy traveling through that wave and all along that wave. And he called that packet of energy a quanta. The plural would be quantum. So maybe you've heard of quantum mechanics or quantum theory. That's just the idea or the study of how these little packets of energy behave in greater situations. There's also a relationship here where we can look at the amount of energy of any kind of light as it compares to the frequency of the waves of that light. So he said that E equals HV, so this is another inverse relationship, where the energy in joules of whatever light we're looking at is inversely proportional to the frequency of that light wave. And it has to do once again with another constant. In the last case, we were looking at the constant being speed of light. In this case, Planck did such a great volume of work and collected so much data that he created this constant that connects these two ideas, energy and frequency, and yet again, he got to name it, and so it's called the Planck's constant. And it's 6.626 times 10 to the negative 34 joule seconds. And it's just a constant that helps us to communicate the relationship between energy and frequency of different kinds of light. Shortly after Planck's contributions to our understanding of light and electrons, came along a gentleman you've probably heard of named Albert Einstein, and he was looking at a lot of the research that other people were doing, specifically looking at how light was, the photoelectric effect and some other studies and experiments that were happening. And he looked at a gentleman who was doing a lot of work with the photoelectric effect called Lenard. And what he said was, if we have this metal object, let's say it's a bucket, I don't know why, but that's the first metal object that came to mind, and we're shining light off of it. Here's our light source, right? And little little electrons are being kicked off all over and being detected by screens and whatnot. He said there can't just be wave motion happening in light, because then there would be waves of electrons coming off, but that's not what was happening. Instead, we were getting these little individual of electrons bouncing away from the object. And so he hypothesized that there must be little particles within the light that were hitting this metal object and therefore knocking off individual electrons. He called those little particles photons, because again, photo is light. And so he said there must be little packets of light energy that have enough energy to knock an electron off course and kick it out into a reflector shield or some other kind of object that senses it. And that would be a pretty reasonable explanation for why individual electrons were being knocked off and not whole waves of electrons. And he has continued on in his experimentation and explanation, and what we've learned now is that these photons do in fact exist, and they travel in little wave patterns. And they are just little energy packets, which means they are not in fact matter. They have no mass, but they do contain variable amounts of energy. So that variable amounts of energy leads us to this equation. The energy of an individual photon is represented by our Planck's constant times the frequency of that photon's wave motion. So if the frequency of the wave, say, is really, really slow or too low, then it isn't containing enough energy to knock an electron off its course. It will just hit the metal object and be absorbed. If, however, the frequency is much higher and it contains enough energy, then it's enough to hit this electron and shoot it off into some new pathway. So what that all means to us and how we can see this happening in real life is we know now that each atom, every type of element, releases characteristic photons. Not every element releases all the same photons, which is really interesting, and we'll talk more about that. But the more exciting part of these characteristic photons is that the energy they have corresponds to a specific color. So if say a red or low energy photon hits an electron and knocks it off course, what we see is this release of red light. If it's a high energy, say blue photon, and it knocks an electron off course, that electron releases energy as it's being, it takes on some of the energy from the photon that bombarded it, and then it releases it as it moves. And we see that as a release of blue light. Commercially, this has been used to harvest, these really interesting signs and all kinds of very graphic and colorful different examples of things. And so we can use this to our benefit now that we know what creates these different patterns and different wavelengths and different specific colors. So that leads us to kind of an explanation of how electrons can move from one pathway to another. So electrons, generally speaking, have the bulk of the energy within an atom, and when they have too much energy, we say they are excited. So the electrons are in an excited state. When they become excited, they have some stored energy, but that energy can't be stored for very long. They will very quickly try to release that energy and get back to their stable condition, which is called the ground state. That's the lowest possible energy condition for any element or atom. Every element has its own ground state, and it has its own excited states. They're unique to each element, and we'll talk more about that as we go. But what you want to remember, kind of the big ideas of this section, are that all photons contain light of different wavelengths, and that those different wavelengths release different amounts of energy. One thing that I didn't mention before that is incredibly interesting, and we'll talk more about in class, but I just want to put it on your radar, is that when you combine all visible light, all colors of visible light, so the whole rainbow, it creates this illusion of white light. So the background of this screen appears to you to be white because it actually contains every single other color of the visible light spectrum. The thing that's interesting is we generally think of this color, black, as a combination of every possible color, right? If you were in art and you took all the different colored paints and you piled them all up, what you would get is kind of a murky black mess. In actuality, this is the complete absence of color. There is no visible light color happening here, and I'll talk to you more about that in class. I have no doubt you will have questions. So just to wrap this up, in looking at different elements, I told you that every element has its own specific energy levels that it can allow electrons to move to. We can see the different levels of electrons by getting the element kind of excited, right? Which usually means we pass an electric current through it, we give it a bunch of energy, and it will create this glow, just like a neon light. If we then move that glow through a prism, which is basically a crystal-shaped structure, it splits all of the different kinds of light into their constituent parts. So let's say we're seeing a kind of a greenish colored light from an element that's being electrified. If we pass that greenish light through a prism, what we might find is there's actually a red band and there's a blue band of light, but they have combined in this pattern to form what we saw originally as just a green light. The breakup of the different colors is called the emission line spectrum. So spectrum tells you the range of colors. They come to us in little lines, just like the ones I've drawn here. And emission means this is what's being released from the element as we look at it through a prism. Because every element emits just certain patterns of light energy bands, we know that the bands must be quantized, which means that each color is specific to a visual light energy, and each photon that's being released must be releasing exactly that same amount of energy, which is why we're seeing specific colors. We're going to do a lab on this later on next week. But for example, when hydrogen is heated up or electrified and then passed through a prism, we see a couple of lines, but we see a very distinct pattern every single time. We see violet, then next to it is blue, then there's a little space, and then green, and then there's a big space where we see red. There are no photons releasing yellow or orange light, so that light is not seen anytime when the hydrogen releases energy. So we're going to talk finally about one last experiment by a gentleman named Niels Bohr, and I think he was Danish. He may have been a Swede, I'm not sure. But he was looking at the exact paths of electrons around the nucleus. So if you look at this picture up here, Bohr's hypothesis was that electrons moved very much like planets move in the solar system. He thought that each electron had a specific path, and that it stayed on that path all the time, and that every pathway had a certain energy associated with it. He predicted that electrons could jump from path to path, so they could, say, go from where Saturn is to the next level in here, depending on the amount of energy that the electron absorbed and depending on which orbits were available to that particular electron. And then when electrons moved from a place of high energy to a place of low energy, the photon would be emitted. And actually, when he did some experimentation with hydrogen, he found that the light bands that were seen when hydrogen emitted photons, in fact, fit this model really well. He was dealing with a one electron model and saying this one electron can move from this path to this path or this path to this path, and there would be different colors of light depending on which path it jumped to. Think of it this sort of like a ladder. You could go from rung 1 to rung 3, or run from the first step to the fifth step. But you couldn't be in between steps. You have to be on one step, and the steps are well defined. When he did his experimentation with hydrogen, it really supported this idea. He did, in fact, see defined bands, and he did see predictable colors every single time. Unfortunately, when he tried to apply his model to other elements that had multiple electrons, it no longer fit. So that's where we're going to stop today. We'll look in more detail about this very soon. Please come in with 3 discussion questions and write a summary of 3 to 5 of the major ideas in this chapter, and we'll talk when I see you next. Thank you.